Namaste everyone, hope all of you are well. This will be the last lecture of Equilibrium chapter. Till yet, whatever the things we have studied, we should not forget, and even in each lecture I have informed you to make notes. So remember, dear students, whenever you are learning anything, you should write that things in your notebook. In the previous lecture, I have already described about the buffer solution and especially about the equation called, I hope you have remembered, Henderson-Hasselbalch equation. In that equation we have learned about the acidic buffer solution and basic buffer solutions, the equations and the formulas. In this video we are going to discuss about the solubility equilibria of the sparingly soluble salts. First of all, as we have discussed in this whole chapter about the equilibrium, as we have started with the chemical equilibrium, then we have divided into the two parts: chemical equilibria, physical equilibria. Chemical equilibria, Lee-Chatterley's principle. According to that, we have discussed on the change in concentration, change in temperature, change in pressure. What are the effects of this chemical equilibria? Then we have discussed about the phase transformations, how they are affecting, like pressure change, concentration change, and temperature change. What will be the effects on these? After that, we have discussed about the ionic equilibria, that ions, acidic, how these weak electrolytes, strong electrolytes, how these electrolytes participate, and how this reaction becomes equilibrium. And now this topic, that is solubility equilibria of sparingly soluble salt. First of all, solubility equilibrium. The name itself describes about solubility equilibrium. What is the name? Name itself says about that what the things we are going to study. Solubility equilibria and then sparingly soluble salt. You know very well the solution. After that you have understand about the saturated and unsaturated solution, right? So in this video especially we are going to discuss the salt which are sparingly soluble and what will be their solubility equilibria. If we can take any equation, if I talk about any salt like barium sulfate, calcium sulfate, any salt you can take. So the solubility of these ionic solids in water varies a great deal. If you are taking any salt, just suppose that calcium chloride only you are taking. So what will happen to this calcium chloride? It is so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. If I talk about the lithium fluoride, then it has a very little solubility, that they are commonly termed insoluble. First of all, you should know that which salt is soluble in the solution and which salts are not soluble or insoluble in the solutions. So according to that, you can easily find out this solubility in equilibrium. The main things which we are going to discuss in this topic is solubility. The salts which are soluble, which are sparingly soluble, which are insoluble. The things which we are going to learn is, as for example, if I talk about any salt to dissolve in a solvent, that a strong force of attraction between these ions, just suppose that lattice enthalpy, must be overcome by the ion solvent interaction. The salvation enthalpy of ions is referred to in the terms of solvation, which always negative. Energy is released in this process of solvation. The amount of solvation enthalpy depends on the nature of solvent. In the case of non-polar solvent, the solvation enthalpy is always small, not sufficient to overcome lattice enthalpy. The salt, consequently, the salt does not dissolve in non-polar solvent. As a general rule, a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy, so that the overcome each salt has the characteristic solubility which depends on the temperature. You can classify the salt on the basis of their solubility. If I talk about slightly soluble, sparingly soluble, what is the difference between the slightly and sparingly soluble? I am telling you. The slightly soluble has greater than 0.01 molarity soluble and less than 0.1 soluble. And the sparingly soluble is less than 0.01. the main things as already I have discussed and I already have said you that the things which you are going to learn is sparingly soluble. बहुत सारे ऐसे सॉल्ट्स होते हैं जो आपको पता होना चाहिए कि अगर इसको हम डिसॉल्व करेंगे तो ये पोलर सॉल्वेंट में डिसॉल्व हो रहा है कि नॉन पोलर सॉल्वेंट में डिसॉल्व हो रहा है, ये सारी चीजें का इंफॉर्मेशन यू मस्ट हैव. As you will have this information, then it's very easy to calculate this solubility equilibria. अभी हम लोग एक इक्वेशन के बारे में पढ़ेंगे that how this equation deals with it. So let's start. I am going to take one equation. That equation will inform us that what is the solubility. Okay. So our main thing which we are going to calculate is solubility product constant. The main topic is solubility product constant. Just suppose a barium sulfate, BaSO4. I am dissolving this barium sulfate into the saturated solution. Okay. So what will happen? This barium sulfate will dissociate into Ba2 plus and SO4 2 minus. Am I right? Because they dissociate into the ions. Now we are going to calculate the solubility product constant Ks. Solubility product constant is equal to concentration of products upon concentration of reactants. So concentration of product means Ba2 plus concentration, SO4 2 minus concentration upon BaSO4 concentration. Are you getting or not? Here you can see, as we have discussed, that dibasic, monobasic, all those things we have already discussed. So here the solubility product constant, as I have taken a salt, barium sulfate, and this barium sulfate, it is in the contact with the saturated aqueous solution. So here saturated solution means in water I am talking, not in other things. So saturated solution in water. So what will happen is, it is in the aqueous solution. So the equilibrium between the undissolved solid and the ions in a saturated solution, it can be represented here, as you can see here, right? So the concentration, the substance, pure solid substance, the concentration remain constant, and we can write here. Now the sparingly, the solubility product constant, if you want to write, then you can just write, because here the things which you are learning is, as we just suppose here, sparingly product solution KSP is equal to KF, and which is also equal to here barium 2 plus and sulfate 2 minus. Got it, dear students? As we have already calculated in the previous video that about the acidic solutions, basic solution, neutral solutions, and amphoteric solutions. So here for a pure solid substance, the concentration remains constant, and we have written the solubility product constant KSP is equal to K into barium sulfate, right? Here one thing which I just want to tell you is, here if you are taking a constant, then it will be just written as like this, no need to worry. The concentration of barium sulfate, okay, BaSO4 is equal to the concentration of barium 2 plus and the concentration of sulfate 2 minus. So here you will not have a doubt that, sir, why it has been written, right? Sometimes you have a lot of doubt because of the confusions. So as I have written here, we can call here KSP as the solubility product constant or simply solubility product. And the experimental value of this solution will be the, just like as we are taking the experimental value of pH value 10 to the power minus 40 at 298 Kelvin. Similarly here, the KSP in the above equation, the value will be 1.1 into 10 to the power minus 10. The value of this KSP will 1.1 into 10 to the power minus 10. Okay. Now you can ask me, sir, here this value, how it has came? This means that the solid barium sulfate in equilibrium with its saturated solution, the product of the concentration of the barium sulfate ion is equal to its solubility product constant. the concentration of these two ions will be equal to molar solubility of the barium sulfate. So if I talk about the molar solubility, then can you tell me? Molar solubility? I'm talking about the molar solubility. So here if I talk about the molar solubility, then here about the barium and sulfate. So here molar solubility S into S is equal to 1.1 into 10 to the power minus 10. So if you want to calculate the value of 1.05 into 10 to the power minus 5. Got it? So here the molar solubility of the barium sulfate will be equal to, if you want to calculate the SI unit, then it will be mole per liter. What will be the SI unit of this? Mole per liter, right? As you have understand about this mole per liter, now a salt may give on dissociation two or more than two anions and cations carrying different charges. Okay, just suppose if I talk about zirconium phosphate, ZrPO3. Okay, ZrPO3. You can ask me, sir, how this S square had came, or S here, S square is equal to S into S. Because you can see here, the charge of barium is also 2 plus and the sulfate is also 2 minus. So that's why here S square is there. If you take another thing like, if I talk about the zirconium phosphate, Zr and PO3, okay, ZrPO3 whole 4. So can you tell me what will be the value? Here zirconium exists in the +4 oxidation state. Here the value will be of zirconium, it will be +4 and PO4 will be +3. So as it will be dissociated, then it will be concentrated as zirconium 4 plus and PO3 3 minus. So here this 4 plus and 3 minus, as we will calculate the 4s and 3s. So total there will be 7s, right? So you can calculate as 3s whole cube, right? And for zirconium you can calculate 4s whole 4. 4s whole 4. Similarly as we have calculated here, okay? Because 1s for barium, 1s for barium and 1s for sulfate. So S into S, so that's S square here. Now, if you want to calculate the solubility constant here, KSP will be is equal to S is equal to KSP. Means constant of solubility product constant is upon 3 to the power 3 into 4 to the power 1 by 7, means 12 to the power 3 to the power 1 by 7, that is KSP 6912. That is KSP 6912. Means if you will take a cube of this 27 into 64, right? Got it, dear students? 4 to the power 4, sorry, I am extremely sorry here, 4 to the power 4, not 3. So here KSP will be equal to, S is equal to KSP upon 6912 to the power 1 by 7. So here the solid salt of general formula MXP plus and XYQ minus. This is the molar solubility as in the equilibrium. The saturated solution may be represented by the, so if you want to calculate any of the equation, any means any, okay? So how you will calculate, can you tell me? MXXY. So here MXXY. So this will be calculated as, now here this is the, means it is a salt, you can say this is a salt. So here if you want to calculate, then no need to worry, XMP plus now anion will be converted as YXQ minus. So this is the method by which you can represent the equation and you can calculate the solubility product constant, right? So here I hope that you have understand. Now we will solve one more equation according to that, so you will never have a mistake that how these things are coming, and solubility product constant will be given, so no need to worry. Okay, and if you want to write the equation about this KSP, then it's very easy. KSP is equal to, okay, now if I want to calculate the equation, then how I will calculate, can you tell me? Just suppose this is the equation, okay? Now solubility constant here, I have to calculate the solubility constant for this equation as the above equation is given. Now if you can see this equation, according to that we are going to calculate the constant value. So here, just suppose, now no need to worry, the equation is mxxy, which is converted to x m to the power p plus and y x to the power q minus, right? So here, you know very well when we calculate the constant KSP is equal to the concentration of product, so mp plus to the power x, right, and x cube minus to the power y upon mx xy. Is it right or wrong? First of all, tell me. Whenever we are calculating anything, by this method only we are calculating the concentration value. Is it right? But for the sparingly soluble solution, so here we don't have to write upon one, means we don't have to write the product one. So here directly, as we have written in the barium sulfate, so easily we can write like this. Yes. Now this will be equal to xs and ys. This will be equal to xs and this will be equal to ys. Now tell me, and what will be the exponent? Can you tell me what is the power of exponent? The power of exponent is same, x and y, right? X and y. So now if I will put this value, now I am going to put this value, so here no need to worry, x to the power x, y to the power y. See here, x to the power x, y to the power y, and s to the power x plus y. Can we write? See here, x to the power x, s to the power x, y to the power y, s to the power y. So that's why a to the power x into a to the power y is equal to a to the power x plus y. So similarly, I have written s to the power x plus y. Right? Now tell me, what will be the value of this KSP? So here, KSP. Now I want to calculate the value of s to the power x plus 1, or I want to calculate the value of s only. Just remember, I want to calculate the value of s. So here, if I want to calculate the value of s, then the value of s will be KSP upon x to the power x, y to the power y to the power x plus y. Is it right or wrong? Tell me. Is it right or wrong? The term KSP in this equation is given by QSP when the concentration of one or more species is not concentration under the equilibrium. Obviously, under equilibrium conditions, KSP will be equal to QSP, but otherwise it gives the direction of the process of precipitations or dissolutions, the solubility product constant of a number of common salt at 298 Kelvin temperature. See, if the equation is given and the value of KSP is given, so now can you calculate the value of S or not? Just suppose we are going to calculate one numerical which is belonging from NCERT, okay, and then we will have a last topic, that is common ion effect on solubility of ionic salt. So let's calculate one numerical. calculate the solubility of A2X3. A2X3 in pure water, assuming that neither kind of ion reacts with the water, the solubility product of A2X3 is given. A2X3. A2X3 KSP value is given 1.1 into 10 to the power minus 23. So here first of all, question is A2X3. So can you tell me how it will be dissociated? A to the power 3 plus and x to the power 2 minus, right? And here the value of KSP is given, right? The value of KSP is 1.1 into 10 to the power minus 23. KSP value is equal to 1.1 into 10 to the power minus 23. So dear student, can you tell me that what will be the value of S here? S means solubility of A2X3, right? So if I calculate solubility of S of A2, means solubility of this A, what will be the value of this? Can you tell me what will be the value of this A? A3 plus 2. Now here one thing I just want to say you is, this will be dissociated into 2A3 plus and 3x2 minus. So if I want to calculate the solubility of A, then it's very easy. S means solubility of A2X3. Solubility of A2X3. S means solubility of A2X3. Now here A3 plus. What is the value of solubility of A2X3 in the value of A3 plus, which is equal to 2S. Equal to 2S. And the value of x2 minus, that is equal to 3S. So total will be 2S plus 3S equal to 5S. Right? So the value of x plus y is 5. Right? So now 2S to the power, if I want to calculate, just suppose dear student, no need to worry. If I want to calculate the value of KSP, what is the value of KSP? 2S to the power 2 or 3. Can you tell me what is the value of 2S to the power 3 and 3S to the power, 2S to the power 2 and 3S to the power 3. 2S to the power 2 and 3S to the power 3. That is equal to 2 2s are 4, 3 3s are 9, 3s are 27, 27 4s are 108. 108 s to the power 5. Right? This is 108 s to the power, and the value of KSP is given. So how can you calculate now value of s to the power 5? It's very easy. I hope if you understand that it's very easy. Because KSP value is 108 s to the power 5 is equal to 1.1 into 10 to the power minus 23. So s to the power 5 is equal to 1.1 into 10 to the power minus 23 upon 108. If you will divide this, then the value of s to the power 5 will be 1 into 10 to the power minus 25. 1 into 10 to the power minus 25. So there are 5 here. So the value of s is equal to 1.0 into 10 to the power minus 5. So this is the value of sparingly solution. Hope all of you understand the value, how to calculate the value of it. Can you tell me what is the SI unit? Mole per liter. Don't forget to write the SI unit. Mole per liter. Okay dear students? So I hope that you can easily now calculate the solubility of any pure substances or solubility product constant. If it will be given, then it's very easy to calculate. Now the last topic of this chapter, common ion effect on solubility of ionic salts. Common ion effects. So if this type of questions will be given, then you can calculate or not. Just check, or if you want to take a screenshot, then you can take a screenshot. Right, dear students? So now the next topic, common ion effect on solubility of ionic salt. What is this common ion effect, Leach-Tetralist principle, have you remembered? The same thing which we are going to express as a Leach-Tetralist principle, that we increase the concentration of any ions, it should have combined with the ions of its opposite charge. And some of the salt will be precipitated till once the KSP will be equal to QSP. KSP will be equal to QSP. Okay? Similarly, if the concentration of one of the ion is decreased, more salt will be dissolved to increase the concentration of both the ions till again the KSP will be equal to QSP. This is applicable even to soluble salts like sodium chloride, except that due to the higher concentration of the ions, we use their activity instead of molality in the expression for QSP. Thus, if you take a saturated solution of sodium chloride and pass HCl gas through it, then the sodium chloride is precipitated due to the increased concentration of chloride ion available from the dissociation of HCl. Now, sodium chloride obtained of very high purity, we can get rid of impurities like sodium chloride and magnesium sulfate. The common ion effect is also used for almost complete precipitation of a particular ions in a sparingly soluble salt with a very low value of solubility product for the gravimetric estimation. Thus, we can precipitate silver ion as a silver chloride, ferric ion and its hydroxide as a hydrated ferric oxide, and barium ion as a sulfur for the solubility of this salt can be calculated very easily. So most thing which you should remember about this topic is common ion effect. First of all, as we have already calculated the common ion effect in the previous video, but then also for this KSP we are going to calculate. Okay, so let's write the common ion effect. KSP is equal to M plus and X minus. Right? Now just suppose for any salt HX, how it will be dissociated? H plus and X minus. Right? If I want to calculate the constant, ions constant value, so you know very well the concentration of product upon the concentration of reactant, right? Is it coming clearly? Just check. Not coming clear? Don't worry. Now is it coming perfect? I think so. Right? Yeah. So here, as you have seen, that the value of H plus and X minus, the concentration of acidic ionization constant, as we have already calculated also. Now if I want to calculate anything from that, just suppose if I want to calculate X minus value, okay? So this is the acidic constant. If I want to calculate here anything H plus or X, so generally if I want to calculate H plus, what will the value? The constant Hx upon X minus, right? With just cross multiplication, nothing more I have done. You can just check it here, that easily you can calculate, right? And if you want to do cross multiplication, then you can write like this here, that H plus x minus, right, is equal to Ka into Hx. Can we write this? Yes or no? Cross multiplication. Now taking the inverse both the side. Now you are going to take inverse both the side. Inverse both the side means just you are going to reverse it. Reverse it means Hx upon x minus. Hx upon x minus and H plus upon Ka. Hx upon x minus. See, just no need to worry. Can see this both are multiplication here, h plus and x minus. So now what you will do about this constant means no need to worry, as I have said you that here can be write like this, h plus upon Ka is equal to hx upon x minus. Can we write this, yes or no? And both the sides as you have taken here, h plus Ka plus 1 is equal to hx upon x minus plus 1. Can you write this? Yes? Easily we can write. Don't forget to give the brackets. So what will be the value here? H plus Ka upon Ka is equal to hx plus x minus upon x minus. Is it right? So this, as you get the equation, now again if you inverse this equation, what will happen? Means again if you are inversing the equation, then the value, the things which you are going to get is x upon x plus hx. X upon x plus hx. This value, as you do the inverse, right? So if you do the inverse, what you are going to get? X upon x plus hx, which is also equal to f, which is also equal to f. And here this again we have inverse, that is Ka upon Ka plus h. Can you write this? Yes? So this can be seen that f decreased as pH value is decreased. As f will be decreased, so pH value will be decreases, and S is the solubility of the salt as given pH. Then KSP. What will be the value of KSP? Here we are going to calculate KSP is equal to S and Fs. So KSP is equal to S and this is Fs. So here we can take Fs square. Can we write this? So instead of F, we can write that Ka upon Ka plus H plus. Yeah, definitely we can write. So here Ss, just suppose here this is the S square, and instead of F here Ka upon Ka plus H plus. Right? Can we write this? Yes or no? Yes, we can write it. So here the value of S is equal to, what will be the value of S? It will be that KSP into Ka plus H plus upon Ka under root, right? Means just see here, my dear friend, this is the value of KSP. So here the S square is equal to KSP into Ka plus H plus upon Ka, right? And if you want to calculate the value of S, the value of S is equal to KSP Ka plus H plus upon Ka under root, means to the power half, that is the value of S. So here you can see that solubility increases with the hydrogen ion decreases in the value of pH. So this is the way by which you can calculate the common ion effect on the solubility of ionic effects. So this is the last topic. You can calculate some numericals as given. So I hope that all the things, whatever the things we are learning in this chapter, common ion effect, ionic effect of acidic, basic, buffer solutions. So these all the things is related to some of the things whenever we go for a higher education like BSc, MSc or BTech chemical engineering or medical science, also in the chemical medical science, there also will get these things to learn how these things dissociated, how this common ion effects value came, how this ionic product solid value came. So whenever you get these things to learn, that time you will remember, because right now you are not getting an application of these things, so you will think that these things are really somewhere we should learn or somewhere we should not learn. But when you learn anything very concentrately, that time the real uses of the education comes. I hope all of you are understanding what I mean to say. If you have any doubt related to this whole chapter from 1 to lecture number 11, 1, there are total 11 lectures in this chapter. If you have not seen any lecture, then you can go through my channel, and in the video section you will see from lecture 1 to lecture 11 you will get all the videos and you can easily learn these things. That's all for today. Thank you very much. Hope all of you have understand. If you have not understand, then drop your doubt into the comment box section, and don't forget to like and subscribe my channel. That's all for today. Thank you very much. Share this channel with your friends so they can be also benefited. Thank you very much.